Hello, everyone, and welcome to this edition of Explore Central Ohio Nature. For this session, we will be talking about the weather. We will be addressing the bigger questions about the weather, not really talking about the things that you see daily on your news reports on television or the Weather Channel or what have you. This is more some major topics about weather, and you will hopefully learn some things you didn't know about. So, the first thing we're going to start with that people always question, and I know I did at one point, why is it sometimes warmer at night, especially during the winter? It's not unusual for the temperatures to, let's say, be in the low 30s during the day for a high. And then at night, it ends up being 40 degrees, 42 degrees. What causes that? Well, the answer is simple, namely greenhouse gases. For the most part, water vapor, carbon dioxide, and methane. They trap heat from the sun in our atmosphere during the day, which slows the radiation of it into space during the day and night. Greenhouse gases achieve this because they are what is known as transparent insulators. And they're not just gases and liquids, but there are other transparent items that allow light to pass through them easily, but some, such as double paned windows, uh, along with carbon dioxide, methane, and water vapor, significantly inhibit the infrared radiation of heat. It inhibits it passing through them. So while it does pass through, it does so very slowly. This means that the Earth's atmosphere will store heat while it slowly radiates it into the atmosphere. There's not enough time during one night for all of it to be radiated. And of course, the sun comes back up the next day to start heating it up over again. So the next thing you might wonder related to that is, what about clouds? Everybody's probably heard that an overcast night makes for warmer temperatures than what you would have with a clear sky. Well, overcast or broken cloud cover, particularly when it is stratus clouds, the higher clouds, they ensure that a nighttime surface temperature will be higher than it otherwise would be. A clear sky paves the way for a chilly night, especially assuming some wind. However, what you may not know is that clouds emit infrared radiation to the ground, which is very efficient at absorbing it. And it keeps the ground as well as the overlying air layer warmer. Now, clouds emit infrared energy in all directions, but in terms of what we're concerned with, it's only what gets radiated downward. Meteorologists sometimes refer to that infrared imagery, energy that's emitted downwards by the clouds and also by the air as down dwelling. You may have heard that term before. To make it a little more clear, think of clouds as space heaters that emit energy towards the ground. At the same time, the ground is emitting infrared radiation up to the clouds, which absorb it. And that keeps their bottoms warmer, especially the more puffy lower clouds. So, in effect, there is a synergy between clouds and the ground at night. That synergy results in warmer cloud bottoms, as I said, and as a result, higher surface air temperatures. So, as you see here, clouds, while they emit infrared heat in every direction, in terms of how it affects us, it radiates down. And when you don't have the cloud cover, you get the chillier nights because infrared heat coming up from the surface of our planet has no clouds to impede it. So it goes more quickly up into the atmosphere. Now, something else related to this that you probably wonder about also, and I know I have in the past, the changes in the wind. And you will have noticed, I'm sure at times, like I did, that wind speed tends to decrease after sunset. And that's because at night, the surface of the earth cools more rapidly than the air above the surface. The air that's in close contact with the ground, about the lowest 300 feet of the atmosphere, it becomes colder than the air above it. The circumstance leads to the development of what is known as a temperature inversion, which is what you see here in the illustration on the right. Inversions dramatically reduce the amount of mixing that occurs between different vertical layers of the atmosphere, especially that closer to us. In consequence, once an inversion sets up after sunset, it is much harder for fast moving air above that layer to mix down to the surface where it would be appearing to us as a gust of wind. So you see on the left here what's labeled as normal conditions, um, mainly when you do not have a cloudy night. Warm air from the ground and from all of our buildings and paved surfaces. They have a free and clear travel up into the cooler air columns higher in our atmosphere. But for what we were just talking about on the right with this temperature inversion, when you have a warm air layer below a cold air layer, any air that is coming up from the Earth, coming up from the planet, um, it hits that inversion layer and bounces back off and heads back down towards cooler air that is above surface level. It's not able to get through that warm air inversion layer. And at the same time, any winds that are in that upper cold air layer above the inversion, it's not able to break through there and get down to us. So that has a lot to do with why we will quite often see winds slow way down or, in a lot of cases, completely stop once night comes. And now the wind overall is pretty important um, to us in nature. And mainly with plant life. When it comes to plants, forests, the wind has benefits. The first thing is what's known as anamortuary, meaning seed dispersal from plants, spore dispersal from fungi, as we've talked about in past sessions, and also dispersal of pollen. And one of the things that happens, and I don't have it on here as a bullet point, is when wind blows on a small seedling or a newly emerged spring plant, it actually helps the plant create a stronger stem. When we did our program on what a plant knows, we found that the plant communicates within itself different things to do in terms of growth or protecting itself based on what exterior cells chemically tell, if you will, internal cells. So each time a plant is pushed by the wind, it releases from its outer cells a hormone called auxin. And auxin stimulates the growth of supporting cells. So that auxin tells the inner cells to grow more structure in support of the outer structure. And from what you can imagine, research has shown that this is beneficial to the plant. And plants that begin growth in the absence of wind, they tend to fall over or break more easily than those grown in the presence of some wind, some regular wind. So that's a part of it. And another thing is what is called mosaic forestation. Some forests experience what are called straight line winds that, as we know, come through a forest and knock down a patch of trees or a line of trees in an area. Now, our natural reaction is to view the loss of trees in the forest negatively, but there is benefit of this disturbance to the forest ecosystem. Um, First of all, we know that downed trees eventually, through the work of certain insects and funguses and mosses and so on, they are broken down and become part of the soil eventually. They also become food for those organisms. The other thing is that it has been found that healthy forest ecosystems typically include a mosaic or patchwork of trees that are of different ages. And it is also a landscape that typically includes a larger variety of tree species. And that habitat supports a greater diversity of wildlife. So it is a benefit to the forest for trees to get knocked down by the wind, because what might have been an entire stand of, oh, let's say oak trees, there is now room and light for other tree saplings that might be in the understory, like perhaps beeches or um, pines or birch or maple. Um, it allows those to grow within that forest. And when you have a variety of tree species like that, it's able to support more varied wildlife species. And today, Humans actively harvest trees to create those mosaic habitats and to mimic the effect of natural disturbances like wind and also fire. This is something that's done in forest management um, in our state, for example, by the Ohio Department of Natural Resources. So, moving on, probably the biggest weather related item that is most often seen by people, but probably most often misunderstood. Remember West Side Story. When you're a jet all the way. We're talking about the jet streams. Jet streams act as an invisible director of the atmosphere and are largely responsible for changes in the weather, not just on our continent, but across the globe, because there are actually four separate jet streams around the globe. They affect other continents besides ours. A jet stream is basically an atmospheric highway located at the level where jet airliners cruise, which is how it got the name jet stream. The main jet streams are located near the altitude of the tropopause layer of our atmosphere, and they are westerly winds, meaning they flow west to east. They do have a little diversity, though, in that they may start, stop, split into two or more parts, combine from separate parts into one stream, or even flow in various directions, including opposite to the direction of the remainder of the jet. And as you see in this diagram here, which should look pretty familiar, the jet winds blow from west to east, but they also, in the process, meander north to south and south to north in a wave shaped pattern, like you see here. Those waves and large ripples are known as planetary waves or also Rossby waves for the scientists that discovered them. And what happens is these U shaped troughs of low pressure form that allow cold air to spill southward, as well as upside down U shaped ridges of high pressure that bring warm air northward. Jet streams are a product of two factors. The first being the atmospheric heating by solar radiation that produces large scale circulation cells. And the other is the action of the Coriolis force acting on those moving masses. And I'm sure everybody remembers from high school science classes, um, Coriolis force is caused by the planet's rotation on its axis plus its magnetic fields. And the proof of that is everybody has heard the fact that um, water runs down a sink or down a flushed toilet in one direction here in the northern hemisphere, but in the southern hemisphere, it runs in the opposite direction. And that's why. The width of the jet stream is typically a few hundred miles, and its vertical thickness is a little less than 16,000 feet. So it's a pretty large body of moving air. They typically are continuous over long distances, like again, we're used to seeing on these weather maps. Um, but what is called discontinuities is also common. Path of the jet typically has this meandering shape that we've talked about. Um, and the meanders themselves propagate eastward, but at lower speeds than that of the actual winds within the flow. So, to look at this just a little bit deeper, here is an illustration of the layers of the atmosphere. And if you see where my cursor is pointing to, here is the tropopause, and just above it actually is where the jet streams are located. Now, to jump away from that for just a minute, we're going to talk about the barometer. Everybody has seen a barometer, everybody has heard the newsman on giving the weather report talking about the barometric pressure. Well, what is barometric pressure? What does a barometer measure? How does a barometer work? How does the weather affect it and vice versa? What does it all mean? Well, this is it. A barometer is a scientific instrument that is simply used to measure air pressure. In other words, the weight of the atmosphere wherever that instrument happens to be. Um, Pressure can forecast short term changes in the weather. Um, there are many measurements of air pressure used within surface weather analysis to help find surface troughs, the higher low and low pressure systems we're used to hearing about, and the boundaries of frontal systems that we're used to hearing about. Now, on the left here is a simple standard mercury barometer, and it has a vertical glass tube that you usually don't see because it's hidden behind a dial. And that tube is closed at the top, and it is sitting in um, an open mercury filled basin. And the mercury in the tube adjusts until the weight of it balances the atmospheric force exerted on that reservoir that it's sitting in. So, high atmospheric pressure, higher weight of the air on the Earth's surface places more force on the mercury in that reservoir, and it forces mercury to go higher up in the column of that vacuum tube. Low pressure does the exact opposite. It eases up the pressure on that basin of mercury and allows, in the process, the mercury within that tube to lower. And there's usually a dial that it controls, which is what a lot of us are used to seeing on a barometer dial that says whether rain is likely or dry conditions or what have you. On the right is a more simple version and actually a later version than what the mercury barometer is, and that's called the Goethe barometer or Goethe weather ball barometer. And it consists of a glass container like you see here with a sealed body that's half filled with water, and there's a narrow spout connected to the body below the water level. And the narrow spout is open to that main vessel. Now, when air pressure is lower than it was at the time the body was filled and sealed, the water level in the spout rises above that of the body. And when the air pressure is higher, the water level in the spout will drop, sometimes even to below the water level in the body. And this type of barometer can easily be made from home. There are a lot of various plans you can find in places like Pinterest and elsewhere online, where you can make one of these Goth barometers from um, a jar and a bottle with a narrow neck, for example, or a jar and a piece of plastic tubing that's sealed at one end. So it's an interesting project. Now, a couple other things about this. The mercury barometer shows us or predicts actually this. Coming back to our maps of the jet stream, you see that area of the country where it says warmer air. As we mentioned, the jet stream around that part of the country is in that inverted U. And that part where the jet stream is moving more northward, that makes for an area of warmer weather. And then when it dips down to the U shape, that means colder weather for that area. So high pressure means warmer, low barometric pressure means colder. Also, coming back to this map, when that jet stream is ascending and making its upside down loop, the ascending sides uh, predict and usually bring with them wet weather, whereas a stream descending downward into that U shape usually foretells dry weather. And I've got it marked here so you can see what indicates wet, what indicates dry. And usually, when you've got an upward sweep of the jet stream um, going along either coast of the United States or of our continent, it typically brings with it wet weather. Now, just a little history on the barometers. This is Evangelista Torricelli. He was an Italian mathematician and physicist. He invented the mercury barometer in about 1647. So in the Middle Ages, um, that was his discovery and invention. And he just happens to have a very cool looking mustache. Unique looking fellow. In terms of the Goth barometer, Johann Wolfgang von Goethe, who lived from 1749 to 1832 in the Weimar Republic, which is now part of Germany, was a poet, a playwright, a novelist, scientist, statesman, theater director, and theater critic. So he was quite the Renaissance man, and we mainly know him today as the creator of that Goth water barometer, which at the end of this presentation here, I will show you one of these, how to make it. Now, what we're going to talk about last is The truth about this stuff, lightning, there are misconceptions about it, and there are things that meteorologists and scientists believe they know about lightning. Um, but there are a couple of different theories, neither one which has really been proven or disproven. They only have science to go on, and what we know about electricity and static electricity and magnetism at this point. Remember from last week's program, um, magnetism and static electricity are two forces of nature that are inseparable. They go hand in hand at all times. So, lightning is what everyone agrees on is caused by static electricity in the atmosphere. It's atmospheric static. Scientists are still trying to work out exactly how lightning forms, but they do know it has to do with interactions between positive and negatively charged ions. When a positive and negative charge grows large enough in the sky, you get lightning. A giant spark of electricity surges through the clouds and sometimes touches down to Earth, sometimes attracts itself to another cloud. Um, but that is what it is. It's a giant electrical surge. And thunder, incidentally, which we'll talk about in more detail in a minute, is the sound lightning makes. And that is because the lightning suddenly increases the air pressure around it and greatly suddenly increases the temperature of the air around it. And it expands the air fast enough that it exceeds the speed of sound, basically. That's what causes it. Now, the crystals of ice and water that make up clouds are actually water molecules. And during a storm, the air moves these particles around, making them collide. According to some current theories on lightning formation, the negatively charged electrons in upward moving molecules of water are transferred to the heavier molecules that are moving downward. And this situation often means that the top of the storm cloud is negatively charged and the bottom of the storm cloud is positively charged. Sometimes it is the other way around. So this is something that's not a total known, although there is something we already know very well about that points to it. We know that like charges and like magnetic fields repel each other. You know, think about the same sides of magnets repelling. If you try to take two magnets and push the north or south poles together, they do not want to touch. Um, because of that, negatively charged ions on the Earth's surface are pushed away, leaving the ground below the storm cloud with an overall positive charge. That forms an electric field, actually, in between the ground and the base of the cloud, just as if it was an invisible wire. That field allows the negative ions to discharge down to the ground while positive charges move upward. And when you look at this illustration here on the left, this is a good example. You have a storm cloud here, and because of this collision of the positive and negative ions as they move around in the cloud, you end up with the top of the cloud being positively charged, the bottom of the cloud being negatively charged, and you have kind of a three-way thing that can happen here. First of all, the um, negative charge that's in the bottom of a storm cloud, because you always have with electromagnetism and magnetic fields, the the difference between positive and negative charges on anything that has a charge, since the bottom of the cloud is negatively charged, as you see here, the ground below it ends up having a positive charge, but only under that cloud. As you see here on either sides of this cloud on the left in the illustration, you've got negative charges on the ground because it's not under a cloud. So what happens is with that negative charge in the bottom of that storm cloud, um, the ions, again, as if in an invisible wire, are allowed to travel from the cloud to the ground in this very high surge of voltage. Now, the second thing you see, which is going on in the middle of that cloud, is there can also be transfer of lightning from the positive in the top of the cloud down to the negative in the bottom of the cloud. And when you see what's called sheet lightning, where you don't actually see lightning bolts, but you see the clouds flashing, that's what's happening. That's this uh, positive electrical charge discharging to the bottom part of the cloud, which is negative. Again, you don't see the bolt because it's obscured by the cloud. It's in there, it's in the middle of it. All you see is that entire cloud looking like it's flashing. That's what that sheet lightning is. And then, as mentioned, in some cases, the positive part of the cloud will discharge its energy northward or upward, excuse me, upward. And then the other thing that can happen and does with cloud to ground lightning is, again, on either side of a storm cloud where the ground is negatively charged, you can get a discharge of energy from that upper positive portion of the cloud all the way down to that negative charged portion of the bottom of the ground of the earth. Then the other thing that you have, um, which we know is cloud to cloud lightning, and that happens when positively and negatively charged ions interact with areas of the cloud, ignoring the ground. Usually it can happen within opposite halves of the same cloud, which again would give you the sheet lightning, but sometimes it shoots from cloud to cloud, and we've seen that too. Cloud to cloud lightning is actually the most common type of lightning. Um, Cloud to ground lightning happens about 10 times less frequently than cloud to cloud. And that is what you see in the right-hand side of this illustration. You have got a positive charge in the storm cloud on the right, and it discharges that electrical energy down to the negative portion of that storm cloud to the left of it. And again, this, as you can see here, um, in both of these clouds, positive energy at the top, which is just like positive energy at the North Pole, positive magnetic force. And on the left here, the labeling of the magnet, North and South poles. And then at the bottom of the cloud, you've got negative. So the cloud looks just like this magnet. And then on the ground under that cloud on the left, where you've got the positive and the lightning strike, again, you've got negative against positive, which is just the same as if you took another one of these magnets on the left, and if you put it on that surface with the negative end of it below the south on the one that you see there, a lot of those shavings around that southern part of the magnet are going to move down and be attach themselves to the top of that second magnet, which would be the north pole of it, just like you see at the top of the magnet that's here. So hopefully that makes sense. Now, something I will point out also, if you've ever seen any of the Frankenstein movies, um, there is always a contraption like you see on the left here, where there is either a glass globe that has lightning flashing around inside of it, or sometimes it is a metallic globe that is on a pole or a shaft that shoots electricity out of it onto something else, usually another metallic ball. Well, this is called a Van de Graaff generator, and it's not something that was created um, by the makers of the Frankenstein movies. A Van de Graaff generator is simply what you see in this diagram on the right. Inside of a shaft, you have at the bottom a plastic, and this is important, materials, plastic pulley that's being run by a motor. At the top of the shaft and inside of the glass or metal ball, you have a metal roller, usually copper roller. And connecting the two rollers is a belt, usually plastic or rubber. And what happens is as the motor turns and pulls the belt around clockwise, a positive charge goes up the left side of that shaft. Whoops, I went too far. Um, Here we go. Sorry about that. The A positive charge goes up that belt on the left side of the shaft, and as it comes around the top of that metal roller, there is what's called a brush, and it's just a thin piece of metal that's attached to that globe, and it collects those positive ions and distributes them into that globe. And then as the belt comes back down, it again meets the plastic wheel, which starts out with a negative charge, but as it rolls, it turns to positive, and those negatives are picked up by a metal brush that's very close to that roller and is actually connected to ground. So this thing runs and it collects up here in this orb the positive uh, electrically charged ions until it can no longer contain what's being put into it. And at that point, it begins to discharge what is this static electricity. This Van de Graaff generator is a static electricity maker. That's what it is, and that's what you see um, in those movies, or you might have seen it in a science class. And this is something that was invented by physicist Robert J. Van de Graaff, who was a physicist at the Princeton University. His first model he demonstrated in October of 1929. And up above his photo there is a picture of one of the first ones would have looked like. And in this case, that larger steel dome, when it discharges that static electricity, its target is that smaller steel ball that you see there on that thin shaft. Now, about lightning strikes and the sound of thunder, I think this is a really good illustration here that explains why you see the lightning first before you hear the thunder. Um, in a nutshell, it's very simple. Light travels at a constant speed of 186,000 miles per second. Sound, on the other hand, travels at a constant speed of 760 miles per hour at sea level, which is 1,100 feet per second. So the light from the lightning is moving a lot faster, way, way faster than what sound waves can move. So you see a flash of lightning, and if you count the seconds between the flash and the thunder, divide the number of seconds by 5, that's how many miles away that lightning was. That's the proper way to figure that out, according to the folks at the Glenn Research Center, which is part of NASA. So, see the lightning, count how many seconds it is before you hear the thunder, however many seconds it was, divide it by 5, and that's how many miles away it was. Now, the next thing I will bring up here is this is, I think, a familiar sight to everybody. What's known as a thunderhead or an anvil cloud. When you see these off in the distance, you know a thunderstorm is coming, and usually a pretty good one. And what I wanted to point out about this is the physics of it. Now, on the left here, this is an illustration of a thundercloud. And you have this storm cloud, and you see on the left, there's something called a mesocyclone. It's just a rotating updraft of air. And it goes up, 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 up through this cloud until it hits the tropopause. And then when it crosses the tropopause um, uh, into the stratosphere, it overshoots the top of the cloud and kind of boils around over. So you have an outflow in either direction of of those water particles, those water molecules, and that's what forms that anvil shape on either side of it. And part of what drives that, as well as driving the rain and the cooler temperatures we get during and after a rainstorm, is while this is going on, you to the right of that updraft from that outflow also have a what's called forward flank downdraft. It's a downdraft of air, and that's what pushes the rain out because those are heavier molecules of water at the bottom because they've been colliding and some of them have combined and they combine to the point that they're just too heavy to remain suspended in the air. Gravity does its thing and the rain starts falling. And then along with that, you've got this cool outflow of air in the direction that the storm is moving. And the interesting thing about this diagram on the right is a diagram of a mushroom cloud from a nuclear bomb. And you pretty much have the same sort of thing happening to a large degree. You have cool air at the bottom, on the inside of the cloud, on the outside of the cloud, being driven upwards into the hot core of this cloud. And in the core of that cloud, um, you've got all these hot swirling gases. Um, and through the center of it, there's an updraft going on. And between the cool air moving up through the inside column of this thing and also from along the outside of it, that churning causes that same shape in that mushroom cloud that's very, very similar to what we see with a thunderhead cloud. And it's the same thing. It's all about updrafts and hot air and cold air moving and circulating. Okay, so at this point, what I am going to do is stop the screen share, and I am going to conclude by the uh, showing you the Goth barometer that I made. And I'm going to start my camera here. So what I did with this particular design, I took a glass candle holder and my tube on this is just a piece of plastic tubing that I've cut at an angle at the bottom so that it's open at the bottom. And then I just sealed the top of it by using my glue gun to glue a soda bottle cap or water bottle cap in place and made sure it was airtight. And the trick about doing this way is you partially fill your glass and then you turn the tube upside down and completely fill it. Then you tip the glass, tip your container as far this way as you can, and then very quickly turn the hose upside down and drop it down in there. And that is how you get the situation you're supposed to have where the fluid in the tube is higher than that of what is in the container. And then for where I filled it, just marked it with a piece of electrical tape and made mental note to myself that when I filled this, the barometric pressure that day was 87.6. So I know that if the fluid goes below that mark, like this, that we've got high pressure and there will be more fluid in the tube. But then when we have lower barometric pressure, it's going to be even or maybe even like this above that line that I marked, and there will be less in the tube than there was to start out with, which when it started out with, it was basically even with the top of this. So we have some higher barometric pressure right now. So this is a very simple way to do it. Fun, interesting little project. This is inside my kitchen for right now, but this is going to be out on my deck near my thermometer and rain gauge uh, once warmer weather comes. So that's the Goth barometer, and I hope you've enjoyed this program. Next week, we will have a program that is going to be about some scientific aspects of biology related to the lives of fish. I chose to do that one because I think, as a lot of people know, we have quite a few different species of fish and game fish here in our state. So stay tuned for that. Thank you for watching.